your daily dopamine with Dr. Joe McCullough. We deliver daily doses of education, entertainment, and inspiration. So sit back, relax, and get ready to be dopamine. Oh, yeah.
All right, looks like we got lots of people joining. All right, welcome to episode 3 of Ask a Physicist Anything, featuring Paul Graham.
Hey there.
Goal, ask Paul some awesome physics questions, and let's sit back and listen to him.
Other kind of physics question.
So, question that we had last week that we didn't get a chance to answer was, how big was the sun when it was initially being formed? So we might thought we'd touch on that for a few minutes, and then also, if Paul wants to, the Nobel Prize in Physics came out yesterday or the day before that. Oh, that was the Neutrino Oscillations.
Oh, that's why you...
So that's why I brought out Neutrino Oscillations. So if you want to talk a little bit about Neutrino Oscillations. And I'm going to be looking at the comments. Hey, Glennie, welcome. I'm going to look at the comments as Paul is explaining stuff. And if you have a question, throw it out there. And if we can't answer it today, hopefully we will answer it next week. Before I turn around, just real quick, my name is Joe McCullough. Talk about how photons get trapped in orbit around black holes. How does that work? Ooh, okay, we'll touch on that one. So anyway, we are doing a weekly series every Wednesday at 3 o'clock Pacific Standard Time. Ask a Physicist Anything. Without further ado, let me give you to Paul. Hey, Paul.
All right, good to be talking to everybody again. Hope you're having fun the last couple of weeks. We had a great time making these things. So yeah, one question that we got near the end of last session was about how big was the sun when it first formed? And the answer kind of depends on what you mean about when it first formed. Let me grab some more colors of pens to do this justice. When you've got a star like the sun, or when you got any star, the earliest stage in its life, and right now we can see this when we see these big giant molecular clouds, as they call them, or stellar nurseries, where stars are just forming right now, is you'll start with a vast cloud of hydrogen hanging out in some otherwise undisturbed region of space. There are, several stellar nurseries in the Milky Way galaxy right now, in our galaxy, that we can see stars in this early stages of being formed. Something disturbs this big cloud of gas. Could be a shock wave from a supernova that went off somewhere nearby. Could just we talked before about dark matter. The earliest structure formation was just bits of this cloud of gas starting to fall into the denser areas in that background of dark matter, or at least that's how we think it would have started. But one way or another, you will have this cloud of gas, might be 10,000, 100,000, million light years across or more. They come in different sizes.
So let's pause for 1 second. For those of you joining late, we are talking about how big our sun was when it was first being formed. And Paul's going through a little discussion talking about that. It's kind of a challenging question in terms of what is the exact size, but Paul's going to give us some awesome results, or some awesome answers. Go, Paul!
All right, and hey, now, I realized while Joe was talking there just now that I'm sitting here prattling away about light years. You probably heard in science classes before what we mean by a light year. It sounds as if it was a time unit. It's not a time unit. It's a distance unit. It's the distance that a light wave or any kind of information can travel in 1 year, but it makes a convenient unit for measuring long distances. By contrast, our solar system right now is a few light hours across. If we're trying to say how big did the sun used to be, if we start by saying how big is the sun right now? So here's a present day shot of our solar system. Well, hell, on the scale I've got here, it would be the tiniest of dots. But the sun itself is about 1/100th of, I'm going to say the sun is about 5 light seconds across, meaning it would take light 5 seconds to cross the diameter of the sun.
If it was moving at the speed of light the whole time.
Going the speed of light the whole time, yeah. It doesn't take light 5 seconds to worm its way out from the core of the sun to the surface. It takes more like millions of years because it's bouncing around like a ball in a pachinko machine. It's not going in a straight line at the speed of light. But if you're going a straight line, speed of light, sun's about 5 light seconds across. And that's not the exact number, kind of a rough estimate. Earth is about 8 light minutes away from the sun. So if I've got the Earth out here, this distance we sometimes say is about 160 million kilometers, but we could just as easily say this distance is about 8 light minutes. So that's the speed of light there, c, times 1 minute. Now, as you head out to some of the outer planets in our solar system, the gas giants, Saturn and Jupiter, you go out beyond that to Pluto, which will be firmly ensconced in most of our brains who grew up in my generation as a planet, no matter what anybody says.
Pluto is a planet!
The New Horizons probe that just passed Pluto, you probably heard about how, it takes just the signals that it was using to talk back and forth to Earth would take 4 or 5 hours for the outbound trip and 4 or 5 hours for the radio signal to get back from the probe to us, meaning the outer edges of our solar system are several light hours out there. Now, once you go beyond our solar system, now you got a gap of 4 light years before you get to the next nearest star, Alpha Centauri. You got a handful of stars within 10 light years of us. So that kind of gives you a scale of how far, both how big the sun is right now, about 5 light seconds across, also known as 1 or 2 million kilometers across, and about how, how broadly spaced stars are out in our sparse region of the Milky Way. It's several light years to our nearest neighbors. And, that would be typical for a star out here in this sparsely populated spiral arm that we're in, is, you got some elbow room. You got a few light years before you run into your nearest neighbor. Now, in this cloud of gas that would have spawned the star, the cloud would be, again, anywhere from, 100 to 1 million light years or more across, depending on the size of it. And at various points in this big cloud of hydrogen and helium and other assorted gases, you'd get denser regions starting to form. So you get all the gas in some neighborhood start to fall inward towards some particularly dense core. Cosmic Reaganomics, I call this sometimes. The rich get richer. That region that used to be a little bit more denser than its surroundings greedily draws in all the gas around it and gets denser and denser.
Because of their mutual gravitational pull.
Because of the gravitational pull, exactly. Now, the region in one of these clouds, so if you ask how big was the sun in its earliest stages, well, you could say back when the little fluctuation that would become our sun was kind of staking out its territory. It was saying, I lay claim to all the gas in this little bubble right here. So we're probably talking about a region of gas that would be on the order of about a light year across. So the sun was pulling in all the gas in this region that would have been, somewhere vaguely around 1 to several light years in radius. So in a way, that was the moment that the sun was first an identifiable thing that was separate from this bigger gas cloud that it was a part of. And how far apart, how big was it at the time? About a light year. How much mass did it have? About the same amount of mass that the sun has right now. One solar mass is 10 to the 30th or so kilograms, I think. But all the mass that would eventually go on to make up the sun and the rest of our solar system would have already been present in that little region that was getting sucked in. Now, the process of letting that region collapse kind of starts out slow and goes faster and faster. I think, this stage from when you first can start to identify that there's a protostar. Protostar is P-R-O-T-O, just meaning kind of the early stages of a star. But from the moment that you can kind of say, I can tell that region's getting denser. There's a star starting to form there. Until it gets dense enough that you can start talking about whether it's ready to fuse hydrogen, that's somewhere around the order of about 100 million years usually. It kind of, the biggest wiggle room there would be, when do you say the process starts? Because it starts really slowly and then picks up steam as it goes along.
So let's pause for 1 second. We have a few.
So my name is Joe, and I'm with Paul Graham. We are both physics instructors at Cabrillo College near Santa Cruz, California, and we're doing a weekly series, Ask a Physicist Anything, or more specifically, Ask Paul Graham Anything, while I get to sit back and enjoy listening to his explanations. He's right now talking about how big was the sun when it first formed, and then hopefully he'll wrap this up soon and we can touch on neutrino oscillations, because the Nobel Prize in Physics just came out and it was awarded for neutrino oscillations. Some people may not know exactly what they're talking about. So can you wrap this up in a few? And then we had a couple questions. So there was a question about time relativity. We did deal with at least some of the relativity from interstellar. We talked about general relativity, but we could certainly go into special relativity and talk about time dilation and things like that. I love neutrinos. Neutrinos are awesome. All right, I'm going to turn you back to Paul, and then...
All right, Paul.
All right, so you got these little regions that are starting to get denser and denser. Some of them are bigger than others. Some of them got more mass than others. What happens next, kind of the fate of the object that's forming at the center of this thing, depends on how much mass they have. If it's a small enough little region, and it's gathering together mass which is less than about 1,000 times smaller than the mass of our sun, then it's never going to become a star in the first place. It's going to form a big ball of gas, much like the planet Jupiter in our own solar system, which is a big ball of gas that's orbiting our sun. If you've got a ball of gas the size of Jupiter, if you got anything less than about 1/1000th the mass of the sun, then it heats up. The reason it heats up is just as this gas falls inward, well, hell, you know, as something falls toward the center of a gravitational field, it speeds up as it falls. Now, these gas molecules speeding up, since they're bouncing off each other, they don't just go into these ballistic orbits where they end up moving like a bat out of hell toward the center. Instead, they bounce off each other and they turn that into randomized thermal energy. So the cloud of gas gets hotter and hotter and hotter as it contracts. If it's the size of Jupiter, it gets real, real hot, but not quite hot enough to ignite nuclear fusion. And it kind of gets as densely packed as gravity will get it. Now the pressure of the gas in the inside is fighting back against gravity to hit equilibrium. And it just kind of stops there and gradually cools off and gets a consolation prize for a nice try at becoming a star, but it didn't quite make it.
Wait, are you saying a planet is just a star that couldn't actually follow through?
Actually, if Jupiter had not formed like in the orbit around a larger star, but it had just been a little isolated object out there, it would not quite have made the cut for being a brown dwarf. A brown dwarf is a star that can barely fuse. The only thing it can fuse is deuterium. It can't fuse regular hydrogen. And it's kind of the least impressive kind of star there is.
Sorry,
Jupiter
brown
would have
dwarfs.
been, hey, when we were talking dark matter, we talked about MACHOs, which was the acronym that was one of the alternative dark matter candidates to WIMPs, weakly interactive massive particles. I forget what MACHO actually stands for. Massive something something
Halo object. Massive. Halo object.
Yeah, but I mean, obviously they made up. They wormed their way into that acronym as a joke because WIMPs already existed. So they were saying, okay, let's go to the contrasting name here. But Jupiter would have been what they call a macho. What those machos were as dark matter candidates were saying, hey, maybe there's just a bunch of balls of gas not quite big enough to ignite fusion, and maybe those are the dark matter. As we told you that first week, that is no longer really a viable idea, but hey, it was something that they considered for a while. Now, if the thing's bigger, then you will get fusion. What'll happen is that cloud of gas, as it contracts, will get so damn hot at the center from all the gravitational energy that it's released that you will start, and this actually feeds right into solar neutrinos.
Perfect.
Hey, so you'll start a reaction that actually will give us the perfect segue to solar neutrinos.
Woo!
You will start a reaction where, okay, most of the gas in this thing is hydrogen and helium, the two most common elements of the universe. What is hydrogen? If you remember a chemistry class, hydrogen is an atom that consists of a single proton and a single electron and a cloud around it. I draw it as a cloud rather than an elliptical orbit because this is quantum mechanics. Things don't follow nice, clean elliptical paths. They form probability clouds. But I would have a single proton and a single electron around it. But in this hot gas at the center of this rapidly condensing cloud, which is falling from what used to be a light year across and is now getting down to several light minutes or light seconds across, getting down toward the present size of the sun. It's hot enough in there, this electron orbiting the proton, hey, it has long since been knocked off the proton, and the electrons are just moving around on their own. The electrons are still there, but they're not bound to any particular proton. Everything's bouncing around so fast that those particles got knocked free from each other. And then you might have this proton, and it finds itself on a direct collision course with another proton. Now, there are two competing forces that govern what happens next. there's electricity. The electrical force wants to repel these things because they both have positive charge. You probably remember from somewhere along the way in school, like charges repel. So you got these two positive charges coming toward one another, and the electrical force is doing its best to deflect them away and not let them get close to each other. There's also the strong nuclear force that does want to bind these two things together. The whole reason why there are elements besides hydrogen, the whole reason why, say, in a carbon nucleus, which would be a little blob of 6 protons and 6 neutrons, the whole reason why a carbon nucleus can exist, because if you think about it, it shouldn't exist. What the hell business do these 6 protons have hanging out in such close proximity to each other if they're all positively charged? They should be flying apart at, accelerating up to pretty close to the speed of light. They don't. The force that holds them together is even stronger than the electrical force. And it was given the wildly uncreative name of the strong nuclear force. You can't argue with the accuracy, but Calvin from Calvin and Hobbes would have advocated strenuously for the giant kablooey force or something like that. But the strong nuclear force is the reason why nuclei can exist in the first place. It's the only thing more powerful than the electrical force and the only thing that can hold them together. So these guys are a candidate for getting bound together by the strong nuclear force. Only problem is, strong nuclear force may be powerful as hell, but it's very short range. These two protons have to end up pretty much touching each other before they can bond together. And they are tiny. When I drew that quick example of an atom a minute ago, I cheated. On the scale of an atom, the nucleus is too small to see. If I built a model of an atom the size of this room that we're in, can you pan the room?
Yeah.
If I built a model of a hydrogen atom the size of this room, the nucleus would be about 1/10 of a millimeter across, so like a tiny grain of sand hanging in the center of the room. So when I say the nuclei have got to touch each other in order to merge, man, that's a very short distance. However, every once in a while, if the cloud of gas got hot enough, and this is why, some things just fail to become stars. They never get hot enough. But if the cloud of gas got hot enough, then every once in a while you will have a pair of unusually, bizarrely high energy protons happen to be headed toward each other. And while the electric force slows them down and slows them down and slows them down and repels them, they still manage to make contact. Strong nuclear force kicks in. And at that point, a whole bunch of energy is released, and you have merged those into a heavier nucleus. Now, I'm cheating here again a little bit. I've now made something with 2 protons and no neutrons. That's not really going to happen. I need to turn one of those into a neutron. And that is the job of the weak nuclear force. So I often when we're first going through this, teach it as if it was a 2-step process. It's not. This step and the next one actually have to happen simultaneously. But these 2 protons now look at each other and say, "Hey, we got bonded together. We released a whole bunch of energy and formed this new strong nuclear force bond." But then nature also says, "Yeah, but the protons and neutrons are way out of balance here. We got 2 protons, 0 neutrons. You want more of a 50-50 balance. That'd be a lower energy state." And as it turns out, there's another force, the weak nuclear force, that is the trickster, the coyote, the Loki figure, if you will, of these fundamental forces. The weak nuclear force is the only one that's capable of turning one fundamental particle into a different one. In particular, at this moment, the way to lower the energy of this newly created pair would be to turn one of those into a neutron. Now, strong force says, that's great. I can exert a lot of force on things, but I can't turn one particle into another. What are you, crazy? Weak nuclear force is that crazy, and it can. So the next step here...
That crazy weak nuclear force.
Yeah, the weak nuclear force is going to turn one of those protons into a neutron. And here's where we get those neutrinos, which are the subject of this year's Nobel Prize, apparently. That reaction, where a proton... So I'm going to write out the reaction here. You started with a proton. It turned into a neutron. Even the weak nuclear force, as much of a iconoclastic rebel as it is, has rules it's got to follow. you can't change the total charge of the universe. And if I just turned a positive charge into a neutral object, I've got to produce something else positive to make up for that. The only light enough positively charged particle to fill that role, and the reason I say light enough is because, hey, mass is energy, as Einstein told us, and if I tried to put something really heavy like another proton in there, you'd say, no, I barely had enough energy to get those two things together. I don't have enough excess energy in this situation to start creating new, heavy, exotic particles, but I do have enough energy to create something very light, which is a positron, the antimatter partner of an electron. So that's just like an electron, but it's made out of antimatter instead of regular matter. And then there's another rule. If I create a member of the electron family, and that is a member of the electron family, I've got to balance every new matter particle in that family I make with an antimatter, and vice versa. So if I just made a positron, an antimatter member of the electron family, I've got to make a regular matter member of the electron family. Now, I can't have it be something with charge, or I'd mess up my charge balance again. I can't have it be something with very much mass because I haven't got enough energy. I barely had enough energy to make this happen in the first place. The one particle that fits the bill is what they call a neutrino. I'm going to give you a quick family chart. The electron is related to several other particles. There are two more massive versions of the electron. They call these the muon and the tauon. Rabi, a physicist from the 1930s, when they first discovered the muon, asked, who ordered that? Why do I need another particle that's just like the electron, but heavier? Well, it turns out for the same reason we need 6 quarks instead of just 2 quarks, we need 6 particles in this chart instead of just 1 or 2 or 3. So there's the electron and its 2 heavier cousins. The next column in the chart, the electron has a particle that goes with it, the neutrino. The mu has a particle that goes with it, the mu neutrino. There's a tau neutrino also. These guys all have no charge.
So we have 3 different kinds of neutrinos, and each one of those has an anti-neutrino partner.
Yes, everything in this chart has antimatter particles. So the electron has the positron as its antimatter counterpart. Neutrinos have antineutrinos, and so on. But the neutrino, it's a member of that top row, a member of the electron family, which is just what I needed to balance this reaction. It has no charge, so it doesn't mess up my charge conservation, and it has damn near 0 mass. In fact, for a long time, they used to think it had 0 mass. That question went back and forth for decades before finally settling on, okay, it's got a little bit of mass. Very, very tiny, though. So the amount of energy it takes to create it is still nicely affordable here. So the last thing that happens is these 2 protons have turned into a deuterium nucleus, something with 1 proton and 1 neutron. Now, the story is going to go on. Now, this has already released a bunch of energy. And the fact that this process does release energy, this is why stars shine. This is where the energy in sunlight or in any kind of starlight comes from, is this process of nuclear fusion that's going on in the core. How did this release energy? Well, I mean, when you form that strong nuclear bond there, that generated some thermal energy. This electron here, this positron, is eventually going to run into an ordinary matter electron, which are plentiful. Remember, I told you, the hydrogen atoms in this core, they've lost their electrons. The electrons aren't attached to the nuclei anymore, but the electrons are still flying around. They haven't gone anywhere. They're just not bound to any particular nucleus. So this positron is very quickly going to run into an electron, and what happens when matter and the mirror image antimatter particle meet? They turn back into pure energy. We said that Einstein had said in order to have mass, you have to have energy tied up in the existence of those particles. Well, the particles cease to exist. And I'm not saying they crush each other and break each other into pieces. No, it's something more radical than that. This electron and this positron will literally cease to exist when they meet. There won't be any debris left over. They'll just be gone. Except that the energy that went into allowing them to exist in the first place still has to be there. So that energy is going to be released as gamma rays. The gamma rays are going to be absorbed by the dense material at the core of the sun, and this is going to be heating up the sun, giving it the thermal energy to remain hot enough to keep doing fusion for a star the mass of our sun, it's got a lifetime of about 10 billion years. Now, this process continues. After this step, I need to take these deuteriums and fuse them into helium. Then for a while, the helium will stay put until very near the end of our sun's lifetime, when even the helium will begin to fuse. So there's more stuff I could say here. However, I want to instead follow what happens next to this neutrino. Now, neutrinos are ghost-like little particles. I told you they have almost no mass. I told you they have zero charge, and that was important to keeping this equation balanced. Well, right away, having zero mass means they don't create very much in the way of gravitational fields. Having zero charge means they don't create or respond to electric or magnetic fields. They also don't feel the strong nuclear force. Nothing in this table of particles does, actually. That's why electrons aren't part of the nucleus, why they're part of that much more loosely bound cloud around the nucleus. Nothing in this table feels the strong nuclear force. By the way, I could make you another table of quarks. These guys feel the strong nuclear force. Up quark and down quark, charmed quark and strange quark, top quark and bottom quark. All of those can be bound together by the strong force into bigger particles like the proton and neutron, but these guys don't. So out of the fundamental forces of nature, if you are a neutrino, what are the forces of nature? There's gravity, but if you're a neutrino, you don't feel gravity, or you don't feel very much gravity, you don't create very much gravitational field. There's electromagnetism. If you are a neutrino, you literally feel no electromagnetism. You have no charge, so you don't know that electromagnetism exists. There's the strong nuclear force. But if you're a neutrino or anything else on this table, you don't know the strong nuclear force exists. What are you left with? Only the weak nuclear force. A neutrino's whole way of interacting with the universe comes down to a very slight ability to create gravitational fields and an ability to respond to them, and the ability to feel the weak nuclear force. And that's it. If you're a neutrino, your life is very lonely. Those are the only two ways you interact with your surroundings. And what do these neutrinos do? They go zinging off from the core of the sun and pass right through the entire sun like it didn't exist. As far as they're concerned, it doesn't exist. The weak nuclear force, the only one that can really use to interact with the sun, is so weak that the chance of that neutrino even once interacting with another particle on its way out of the sun are pretty much zero. In fact, I think if I remember the anecdote right, if you built a wall of lead, I think
light year.
I was going to say 4 light years thick.
Yeah,
but
I've heard the average neutrino can pass through a light year, so 6 trillion miles of lead without interacting on average.
Have a 50-50 chance of having interacted once by the time it's through that complete ridiculously thick wall of lead.
So actually a really good topic for a future scope might be, so how in that world do we detect neutrinos if they're going to pass through 6 trillion miles of lead without interacting?
I wish I could say something really, really clever about how we do it. The actual answer is sheer patience. If I have a neutrino detector, then for every 10 to the 22nd, 10 to the 23rd, 10 to the 24th neutrinos that pass through it, one of them might interact, depending on the design of the detector. And I just have to send so many neutrinos through that I notice the signature of that one that does interact. It ain't an easy thing to do. For a long time, whether neutrinos even exist was a focus of fierce debate in the particle physics community. But they do exist. They can be detected with enough patience. And interestingly, there should be a fairly large flux of neutrinos from these reactions in the sun. Again, all of the energy that the sun generates each day is powered by these fusion reactions. So in order for the sun to keep generating energy, it's got to be spitting out a whole lot of these neutrinos. We can detect them on Earth. These neutrinos, we said, they're so light that they are moving at very close to the speed of light. So we said Earth is about 8 light minutes away from the sun. Well, it takes these neutrinos about 8 minutes to cover that distance from the sun to the Earth. What do they do when they hit the Earth? Ow, neutrino just hit me. Well, no, I don't. It did, actually. Many neutrinos just hit me. I don't notice them. They pass through me as ghost-like as they pass through everything else. They really don't hurt me. Not not even in the sense that other high, X-rays or something, if they were passing through me, might hurt me. They leave kind of a little trail of devastation on the molecular level as they go through. Neutrinos don't. They pretty much don't interact
ghosts
at
do
all.
exist.
So
do you know offhand about how many neutrinos pass through your body every second?
I am going to say I would make an estimate of 1,000, and I'm going to say I could easily be off by several orders of magnitude in either direction. I am going to say this is the kind of problem, a Fermi problem.
Somebody says
How many
1
neutrinos?
trillion.
A trillion?
Okay,
I was off by 6 orders of magnitude. Then. It was worse than I thought.
Thank you, Legendary Woo. Is that, do you know that for a fact? I'd heard something like that too. I don't know the exact
the way you can do it
numbers
as a
on that.
Fermi problem is you just figure out how much energy the sun's giving off. I'll get you started. We get about 1,000 watts per square meter falling on the Earth, and we know how far the Earth is away from the sun. Figure out how much energy the sun's giving off. Figure out how much energy each of these fusion reactions gives off, and actually fusing 2 protons and going all the way along the chain to helium. So I would have had to finish this story and get this deuterium fused safely into helium. 2 protons going to helium gives you about 10 electron volts of energy, so about 10 to the negative 18th joules of energy. From that, that's enough to figure out how much, how many neutrinos the sun's giving off. From there, you could figure out how many are hitting us per square meter. You could also even get clever and say, how many photons of visible light does the sun have to give off for each neutrino that it gives off? And just figure out how many photons are hitting us in that 1,000 watts per square meter and scale from there. So yeah, there's ways you can do the estimate. I have no reason to doubt that number of 1 trillion, but let's all do the Fermi estimate and meet back here next week and compare methods.
Okay, so we're going to have to wrap this up in about
So the quick thing,
3 or 4 minutes.
Okay. So
Which
these
means we may
neutrinos
not get to
we should
oscillations.
be seeing from the sun. We do see neutrinos hitting us from the sun. Not as many as we should have. The flux of neutrinos from the sun is considerably smaller than it ought to be to explain the amount of energy that the sun's giving off in fusion reactions. For a few science fiction writers, this became the basis of some stories of various qualities saying the fusion reactions of the sun must be going out, and that's why we're not getting enough neutrinos from them. We were pretty sure the fusion reactions of the sun are not going out, both because stars don't really work that way. I mean, we can see main sequence stars at every phase in their lifetime. They don't just die for no reason. Also, just because, man, what are the odds of humans coming around right at that eye blink of geological time when the sun happens to be going out? That would be like a weird coincidence. So no, we figured the fusion reaction is not burning out, and in fact, it's not. What's going on is, remember, there's 3 different types of neutrinos. Because neutrinos do have a little bit of mass, and because each of these has a different amount of mass, this lets you set up these neutrino oscillations, as Joe was calling it. What ends up happening is, out of these 3 types of neutrinos, the only one that these fusion reactions should be giving off is the electron neutrino, because they're being created to balance these positrons, these antimatter electrons. So you need to create another member of this same row of this chart. So when those neutrinos are created, they're electron neutrinos. As it turns out, though, electron neutrinos do not have to remain electron neutrinos forever. You get this gradual oscillation where an electron neutrino can change identity and become a mu and a tau and back to electron. Why does this happen? Man, I'm glad we're almost out of time, because we were just, in another context, we were just hanging around in the stockroom before this started and arguing among ourselves of what's the best way to explain how neutrino oscillations work. And man, we did not reach a conclusion, but by next week we might. So the quick answer is it comes from the fact that the neutrinos do have unequal masses. It turns out that in quantum mechanics, you are looking for what they call an eigenstate, which is what it's like a state that a piece of matter can be in that has a well-defined energy, and once you're in that state, that's a permanent solution to the quantum mechanics equations, and it'll stay that way till disturbed. The mass eigenstates of these neutrinos is a little bit different from their what they call flavor eigenstate, their identity eigenstate. Something that's a perfect electron neutrino with no mixture of mu and tau superimposed in quantum mechanically is not quite in the most stable mass state. It's a little bit off. And it turns out that these guys want to stick in the long run in a stable mass state, which means that that electron neutrino will have a tiny bit of tauness superimposed in that quantum mechanical probabilistic way that we always have so much trouble finding the words from, and a little bit of munus superimposed in. And over time, that wave function can oscillate smoothly between those three states. Why are we getting so few electron neutrinos hitting the Earth? Because in that 8 minutes it took them to travel from the sun, and I mean, in particle physics, 8 minutes is a goddamn lifetime. It's practically geological in time scope. So even though the electrons were only a little bit off from that pure flavor state, that was enough that over that vast 8-minute time scale, yeah, they were able to oscillate so that by the time they reach the Earth, only a third of them are still electron neutrinos. They're pretty much evenly mixed between those three states. And that turned out to be the solution to that solar neutrino dilemma. And to go any deeper, I would have to even more start saying, oh damn, how do I phrase this, man? Do I even understand this myself? Help, I'm totally, which means I am so glad that we're out of time. No, I'm sorry we're out of time, but I'm glad that I get off the hook and can collect my thoughts on this one before next time.
All right, so thank you, Paul.
Okay, my name is Joe. I'm the physics program chair at Cabrillo College in Santa Cruz, California, and we were just enjoying Paul Graham explaining. Definitely a treat. Yes, as always, they love you, Paul. We touched today on a little bit of some solar physics. How did the sun form? How big was it when it was initially formed? And also we touched a little bit about neutrino oscillations. A couple of questions that came in for next week. Time relativity. So we can talk a little bit about special relativity. What happens as you start to approach speeds near the speed of light?
All right.
You probably know
That's one of my favorite questions.
time slows down. Super cool. As far as we know, time only moves forward. You can't go backwards in time. But time doesn't have to move forward at the same rate for everybody. Meaning 1 second for me may not be 1 second for somebody else if they're traveling at speeds, actually any speed, to be honest. But it's only really noticeable at speeds near the speed of light. And then somebody else had a question, just gluon, or just gluon question mark.
Okay, well, we said that the strong force, that one of its jobs is to hold those quarks together to build things like protons. Gluons are the messenger particles that carry the strong force. But we can definitely go a lot more into all of these fundamental forces. But yeah, when we talk about the strong force, gluons will be part of that story, yeah.
All right.
So the goal was to keep these to about 30 minutes. We're about 42 minutes in today. Yay, Donna Matrix.
We're not doing too bad. We're not orders of magnitude.
Believe me, if I was willing to scope for 5 or 6 hours, Paul would be here talking the entire time. Thank you guys. You are so welcome. So again, my name is Joe. I'm on Periscope every single day. Wednesdays is Ask a Physicist Anything. Tomorrow, I'm going to finish up with my series on the alpha state process, how to get in the optimal brainwave state for learning. And then on Friday, I'm going to show you a very cool physics demo. I meant to show it last week, but we got liquid nitrogen, and anytime I get liquid nitrogen, I gotta show that kind of demo. So what I think I'm going to show on Friday is, you guys make me want to change my major to physics. Oh, Donna, thank you so much. I love it when students take a conceptual physics class and there's no math, and they get so excited by physics that they literally completely change their major into physics, which means they have to catch up on the math. And anyway.
But the great thing is a physics major can leave you with like a style of thought that then pays off in any walk of life. You don't need to stay in physics forever to make it worth studying.
Okay, so that is it for today. Thank you for joining. We'll be here next Wednesday, 3 o'clock Pacific Standard Time. Ask a Physicist Anything with Paul Graham. All right, have an awesome Wednesday, and hopefully I will see you tomorrow.